everyone. Today, I, Arushi Sapra, student of Chitkara University in the Department of Electronics and Communication Engineering, is going to represent a paper on voltage-based, energy-efficient mobile charge sensor design using LV-CMOS input-output standard. So, what all points I am going to discuss, firstly about the introduction and the need of design, comparison tables, overall comparison of various input-output standards, conclusion, and finally its future scope. In today's world, every single person is having an Android or a smartphone. But the major problem related to a smartphone is its battery usage. Generally, a smartphone battery prolong for 8 to 10 hours. But we often see a message of battery is low. Please charge your mobile on the phone. So, to improve the battery efficiency of a mobile, I have designed a paper through which I compared various parameters like power dissipation on which we, through input-output design, through which we can increase its power efficiency. Now let's discuss what is regarding the paper. In my paper, what all is this research paper about? An approach is made to design the voltage-based, power-efficient, energy-efficient mobile charge sensor design. For the reason, that's why I have used LV-CMOS, as it has a very high efficiency. Power dissipation is considered to be the main factor. The coding in this paper has been done on Verilog on 28 nanometer FPGA, that is Kintex 7. Now the question arises, what is Kintex 7? Kintex 7 is 28 nanometer FPGA on which we are implementing our design to reassure power reduction and reduction in temperature in sequential circuit. The performance of the sensor is tested and evaluated through the software, which is Xilinx. Now, why we have used Xilinx software? It has low power, high performance, high value for any FPGA family. It is easily configurable as well as ready to use as IP cores. The quality of our sensors can be improved by using various other input-output standards. Now, why there is a need of this mobile charge sensor design? This research work is basically being done to check the charging status of a mobile phone. I have researched about the various frequencies of different mobile phones on which they operate. Like Nokia Lumia 710 operates on 1400 MHz. Samsung Galaxy Core works on 1.2 GHz. iPhone 6 works on 2100 MHz. HTC T on 1700 MHz, Micromax X091 on 1800 MHz, and Sony Xperia Z on 2.2 MHz. High performance mobile charge design is current research area. But there is no specific research being done on the energy efficient charge sensor design. So, to continue further, this research paper is basically stretched on a voltage-based efficient fast sensor using 4 different kinds of stubs, which are stub series terminated logical input-output standards. Okay, so voltage sensor is operating on different frequencies at temperature 25 degrees Celsius. Input-output standards which are being used. We are operating our sensor at 25 degrees Celsius, and LV CMOS family like LV CMOS 33, LV CMOS 15, 18, 25 and BLVD S2515. Input-output standards help us to achieve significant energy efficiency. So that's why we have used a particular family and its members. Performance is evaluated by performing simulations on a magnetic recording channel. This is the criteria on which the voltage in a mobile phone is basically being designed. Like, if the voltage level increases beyond 3.7, it is considered to be an overcharged. If the voltage level lies between 3 to 3.7, then it is full charged. If the voltage level lies between 2 to 3, then it is optimal charge. And if the voltage level lies between 1 to 2, it's medium charged. If the voltage level is 0 or 1, then it's low charge, and if it's completely 0, then it's discharge. So these are the comparison tables which I have calculated on the Xilinx software. Firstly, this first table which shows about power dissipation on LV CMOS 33 input-output standard. In this table, it can be seen that at 1400 MHz, there is a power reduction of 4.54%, and at 2.2 GHz, the power reduction is increased to 18.6%. The in-between frequencies lie as 13.28% to 10.25 and 12.25% at 1800 MHz. The next power dissipation table is of LV CMOS 25 input-output standard. In this, at 1400 MHz, the power dissipation reduces to 3% and which further reduces to 14.91% at 2.2 megahertz. Next is LV CMOS 18. At 1400 MHz, the power dissipation is 2.12%, and at 2.2 GHz, it's 12.38%. Next is LV CMOS 15. In this, the power reduction is 2.1% at 1400 MHz to 10% at 2100 MHz and 11.76% at 2.2 GHz. Last, which is the most effective input-output standard, which is BLVD S25 input-output, then in which the power reduction is 1% at 1400 MHz to 4.20% at 2.0 GHz. This is the final comparison table which shows the power dissipation at 25 degrees Celsius at different frequencies. As it can be shown that there is a reduction of 4 to 19% at LV CMOS 33 to 1 to 5% at BLVD S25. So from this we can conclude that the least power dissipation is found when the frequency is 1.2 GHz. There is like as I told, 4 to 19% reduction in power dissipation with LV CMOS 33 and power reduction of 1 to 5% in with BLVD S25 when we use 28 nanometer FPGA. We have used FPGA, which is the field programmable gate array, comprises of matrix of gate array logic circuitry, which is reconfigurable implementation of hardware for software applications. Least power dissipation range is 1 to 5%, which is when we use BLVD S25, and maximum power dissipation range is 4 to 19% when we use LV CMOS 33. Now, what's the future scope? Like as I told here, we have initially used to sense the battery of a mobile phone, which we have implemented as schematic on 28 nanometer FPGA, that is Kintex 7. We can further extend our research by using other FPGA families like Automotive Arctic 7, Automotive Cool Runner 2, Automotive Spartan, as Spartan has low cost and high power efficiency, so it can be further used. Vertex 5, Vertex 4 and Vertex C are other families which can be used. So we only secondly we only focus at only one temperature, that is 25 degrees Celsius. We can further change the temperature and enhance the quality of a charge sensor. Here we are only using LV-CMOS. So there is a wide scope to use other input-output standards like LV-DC1, SSTL, HSTL and LV-TTL. TTL family is considered to be more power efficient than the CMOS family. So we can further develop it. Thank you so much.